Hello, and welcome to Team Moon Pie's 2019 presentation. My name is Zachary Marion, and I'm this year's team lead at Embry-Riddle Aeronautical University. In this presentation, we'll go over the safety, the system goals, design philosophy, design process, and team management. I'm going to go ahead and start it off with the next year's team lead.
Thank you, Zach. My name is Nathan Rose. I'm the team lead for this upcoming year. The first thing we're going to be addressing is safety. So we have two safety officers, Connor Scala and Cameron Severin, and during any test we require that two safety personnel be present. One that will watch the robot and one that watches everyone around to make sure that no one goes near the robot during a test. Before a test is announced, we announce it to everyone in the room, and then we post signs in the area. That way everyone walking into the area will know that a test is in progress. Safety officers are in charge during a test, and everyone is required to listen to them. In addition, the safety officers are also in charge of the e-stop, and it is on top of our robot to help minimize injury during a test. We also require that safety glasses are worn at all times during tests, and now I'm going to introduce the mechanical lead for next year.
Thank you, Nathan. My name is Roman Morozov, and I'm the upcoming mechanical lead. With our new Rex design, the goals of the system are to traverse through the obstacle field, mine in the designated zone, and return back to the depositing zone. We were allocated 50 kilograms for our whole system mass, but we are aiming to go under 40 kilograms. We were provided a certain volume. However, our final design for the robot is 1.25 meters by 0.61 and 0.4 meters. Other items that we aimed for include 60 watt-hour of power, 400 kilobits per second of bandwidth, and an operating voltage range of 24 to 57 volts. Our goals were improving from last year by minimizing the increase in mass of the whole system, implementing passive shifting, and designing the system for full autonomy. Our robot must be safe, because safety is our #1 priority. The system must mine at least 5 kilograms in 10 minutes run that was provided to us. The robot must fit within the volume that is mentioned on the slide. The system must be dust resistant, robust, reliable, and capable of teleoperations and autonomy.
So we split our team into 3 sub-teams this year: a mechanical sub-team, an electrical sub-team, and a software sub-team. Each of these sub-teams had a sub-team lead who reported to the team lead, and all decisions that were made by any sub-team had to be approved by the team lead and the faculty advisors. We also split our robot into 5 subsystems: a drivetrain subsystem, sensor suite, chassis, electrical box, and excavation. We put members from the different sub-teams into different subsystems. That way we could maximize the flexibility while maintaining our team structure and maintaining individual responsibilities. In addition, if we ever had issues, we could talk to the Robotics Association at Embry-Riddle, because there are several other teams at our school that are also robotics competition teams that have similar design philosophies and software.
This year, we implemented a legged design by trying to maximize our reliability of traversing the field to get over the craters and across the boulders. And we actually used a prototype leg made out of a cedar wood, and we wrapped it in fiberglass to increase the durability. And the software plan, whenever we started the process this year, was to have 3 points of contact at all times so that we maximize the stability of our system.
The final product of our system was a fully functioning robot with some prototype parts. The final design includes an excavator, which consists of 1 arm and 2 drums. This excavator system is on the inside of the robot when compared to the outside, which we had on the last year. The arm is being powered by a gearbox motor system rather than a linear actuator that we used last year. And another gearbox motor system would be powering the belt that goes inside the arm that will rotate the drums. When drums rotate counterclockwise, they dig. When they turn clockwise, they will be depositing. Right now the arm is positioned in the depositing position, and then when we be digging, it would be lowered down. We switched the orientation of the drums from last year in order to maximize our range of depositing. We had some trouble with torque rating of our motors and structure of the chassis. In order to overcome the chassis structure problems, we added this board during our tests. What happened was our chassis was long and narrow, which created torsion whenever we were running tests of our legs. And this board minimized that torsion. For our final design, we designed extra structural support for the chassis. And in order to overcome the torque issue with the motors on our legs, we added extra gearboxes to each of the legs.
In addition to the gearboxes, we also implemented a couple of software fixes that would also temporarily help us solve the torque problem. So what we did is we had all 6 of the motors lift up the robot and lean as far forward as they can, and then we would flip pairs of motors at a time. That way we would always maintain 4 motors on the ground, and when we were lifting the robot, we would have 6 motors in contact.
These engineering solutions allowed our robot to be able to traverse and mine efficiently. Currently, we're working on the next year's design. While having all of this year's success and failures in mind, we want to redesign the chassis so that we would not need to add extra support. In addition, we want to create a deployable system where, in order to use the time provided to us more efficiently.
So we used some management techniques such as a Gantt chart to help us keep our deadlines all squared away. So we have several review presentations throughout the year. We have the systems integration review, operational readiness review, and critical event readiness review. And these reviews were performed this year in addition to last year because the idea for this system was begun last year and continued on into this year. During these reviews, all members were invited, and we explained the state of the robot and accepted advice from anyone who was present. We also prioritized the drivetrain subsystem this year over other subsystems due to the fact that the drivetrain is a new experimental system, unlike our excavation system, which was used in previous years. So our budget this year was $14,500, and we went over by about $2,000 due to the unforeseen circumstances such as our motors having torque issues and our frame having structural issues. But we ended this year with a fully functional robot, and we learned many issues that we can apply for next year.
And I want to go ahead and give a special thanks to all of the organizations that are on the screen that helped us. So without their financial assistance and other advice that we received from them, we wouldn't have been able to complete our system this year. As far as the performance of our system, if you'd like to check out any of our functionality, you can look at our proof of life, which is going to be linked in the description below. And I want to send a special thanks to everybody at NASA for allowing us the opportunity to present in the NASA RMC competition.